Hi guys, today in this video we'll talk about the linear momentum. So next please. A momentum is a quantity. It's a vector by itself, so it's a vector quantity, but it gives me information or expression about how much motion I have physically. So we say momentum is a quantity, and as I told you, it's a vector quantity that expresses the amount of motion, of course with direction, because it's a vector an object has. Its definition is P, which is the momentum, is equal to mv. M is the mass of the system, which is how hard you can accelerate the object. If the mass is very high, it's harder to accelerate it. That's the meaning of the mass, multiplied by the velocity. And you know what the velocity is from previous labs. So P is linear momentum, and m is the mass, and v is the velocity. Newton's first law of motion. Today I'll be explaining to you the three laws of motion for Newton, or three Newton's laws of motion. If you understand these laws, you'll understand better about the linear momentum because it deals with it seriously. Any object keeps, that's the first law, any object keeps stationary or moving with a constant speed in a straight line. Constant speed in a straight line means constant velocity. Unless external factors, we call them forces, change its kinetic status, which means its linear momentum. So any object, if it's stationary, it's not moving, velocity is zero, and that means the value of the momentum is zero. If it's moving with constant speed in a straight line, which means constant velocity, so it has a constant momentum. If I want to change this value of the momentum, which is mv, then I have to apply an external factor. We call it force to change this kinetic status, which means to change its value of linear momentum. The second law, Newton's second law of motion says that the net force or the net external force on an object is equal to the change of its linear momentum or the change of its kinetic status. So if I have an external factor, which is the force, maybe I'll have one force, two forces, three, and so on, but I sum them as vectors together and I get the net force. So the net force will be equal to the change in the momentum with time. If there is a change, there is an external force or net external force. If there is no change, there is no net external force. So the change in the momentum period of time is equal to the net force on the system. And because P is equal to mv, then okay, the change in the value of mv is equal to the external or the net external forces on the system. And for a constant mass, which is the case that we are dealing with in this lab, then I cannot say, okay, d over dt for the m by v, which is the multiplication rule, plus m by dv over dt. Just, I forget about the change in the mass if it's constant, and that's what we deal with in this lab. So the mass is constant, I can take it out of the derivative, and so I have that the net force, which is the external force in the system, is its mass by the change in the velocity. And the change in the velocity is equal to the acceleration. And so I get the second law of Newton, which is the total net force on the system is equal to the mass by the change in velocity with time, which is equal to the mass by the acceleration, the law that you know well. Now this is the Newton's third law of motion. It says that for every action, which means a force, there is a reaction, which is a force of the same kind, equal in magnitude and opposite in direction. So if I apply whatever force to an object, I call this the action. There will be a reaction, which is another force with the same magnitude and the same in opposite direction. So action or reaction are on two different objects. So if I push the wall, for example, I give a force from me to the wall gives me back the reaction. So the action is from me on the wall, but the reaction is from the wall on me. Suppose that the action and reaction are on the same object. So every time I apply a force on an object, some reaction comes from nowhere in the opposite direction. So all the time you will find that the total force on any object will be zero. So nothing will move and the universe will be spoiled. So the action and reaction are all the time on the same object. On different objects. The action and reaction are called pair. So we say, okay, there are Newton's third law force pair. So if I specify what the action is, what the reaction is, I say, okay, these are Newton's third law force pair. Okay, I'll give you some examples for the actions and reactions. So the first example is this kid. He's kicking the ball, at the time he's kicking the ball, like at the time his foot is in contact with the ball, then I say, you kick a ball, or the kid kicks a ball, the force on the ball by your foot, or the kid's foot, is equal and opposite to the force on your foot, or on the kid's foot, by the ball. And I made these two arrows to express these forces, and the notation we used before is used here as well. So the force on from, so the force on the ball from the person, which is this one, and this is the force on the person from the ball. This is upwards, this will be downwards, and I made sure that these links are the same. So the magnitude is the same exactly, and the direction is totally opposite. This is an action, this is reaction. When you want to know if this is action or reaction, or you want to know that these forces are really Newton's third law force pair, then you will find if BP, PB, they will be flipped. Like if it's AB, it will be BA. If you have force AB and another force BA, that means that these forces are Newton's third law force pair, like the action and the reaction. Another example, the Earth exerts a gravitational force on you downwards, and you exert a gravitational force on the Earth upwards. So it attracts you downwards, and you attract it upwards. These two forces are of the same kind, because I said to you, like, if we have action or reaction, which is Newton's third law, the action or reaction are equal in magnitude, opposite in direction, on two different objects and of the same kind. So the Earth makes a gravitational force on the person makes a gravitational force on the Earth, so both are gravitational forces. The force here is force on the person from the Earth. The force on the Earth from the person. You can see that the indexes are flipped, and these are action or reaction, really. The third example is for a book. So a book on a table, the normal force on the book compresses the table downwards with, like, it compresses the force of the book. There is a force of the book on the table. It compresses the table with itself. I mean, that's why I said with. So due to its weight, because the book has weight, then it will start to go downwards. But the table is there, so it will compress it by a force from it. It's a normal force, but downwards. This force will be equal and opposite to the normal force of the table, or the table exerts on the book upwards. So the book has weight, it will go downwards, but there is the table, so it will compress the table downwards with a normal force. It's F on the table from the book, and the table by its turn will make another force, also a normal force, upwards on the book from the table. These are two normal forces, two contact normal forces, opposite in directions and equal in magnitude. These are a Newton's third law force pair. Okay. So we can now, after explaining these laws, the first law of Newton, which is any object stays stationary or moving with constant velocity if no external forces are exerted on it. The second law, the total force on the system is equal to its mass by acceleration. And the third law, like for every action, there is a reaction, equal in magnitude and opposite in direction. The action or reaction are in two different bodies. The action or reaction are of the same kind. Then we come now to talk about the linear momentum, or the conservation of linear momentum. We define the linear momentum to be the mass multiplied by the velocity of an object. Let's see what the conservation of linear momentum is and why it's conserved. So for a system of objects, maybe we have balls, maybe we have a person and a table and a book, whatever system we have of objects, if no net external force is applied on the system, and so the only forces are the internal forces on each object in the system due to the other object, then, like suppose we have these objects, suppose 5, 6, whatever, and there are exerting forces on each other. And there are no external forces, like out of the system or coming to the system. So the total force will be like from object A on object B, from B on C, from C on A. These are called internal forces. So the net force, the external net force is 0, but the forces are coming from the objects on each other. Then, as for each force, there is an equal and opposite force, according to Newton's third law. The total force is 0, because if object A makes a force to the right on B, B will make a force to the left on A, equal in magnitude. And you can see it's opposite in direction as we explained. So the total force in this system will be 0. And as the total force is 0, then I have that the net force is 0. And because the net force is equal to the change in the linear momentum, that means that the linear momentum doesn't change. Like d over dt for something is 0. So the change in something with time is 0. That means this thing doesn't change. And that means that this thing is equal to constant. So if no net external force or external forces are applied on the system, just internal forces, and we know from Newton's third law that the internal, for every force there is another force, action or reaction, they cancel each other totally. The total force will be 0, and then the momentum will be constant for this system of objects. And then we say, okay, P, the total linear momentum in this case, will be conserved. If we have external forces, it will not be. But if there is no net external force on the system, then the total linear momentum for this system will be conserved. Okay, this is an example for a case that could happen. We have two balls. The first ball is the green one with mass m1, and the other one is a purple and with mass m2. The first one and the second one are going towards each other. Of course, they will collide after some time. The green one is going to the right with velocity v1i. I means the initial, so it has v1, its initial velocity, to the right, and the other one is coming to the left with v2 initial. After the collision, then the purple one, of course the masses are the same, will go to the right in this case, and the green one will go to the left. We do know information for now about how much v1 initial and v2 initial, v1 final, v2 final are. But what we know is that because at the time of collision, at that time, there is a force from the green ball on the purple ball, and another force from the purple ball on the green ball. These are action and reaction. These are equal in magnitude and opposite in direction. So the total force on the system, which consists of the two balls together, is 0. So the total momentum of this system, which is the two balls together, is constant. And so the momentum before this collision must be the same as the momentum after the collision. So I say here that P total, which is the momentum before, is equal to the total momentum after. The total momentum before is the first mass by its velocity before, plus the second mass multiplied by its velocity before. That's the total momentum before. The total momentum after is the first mass by its velocity after the collision, plus the second mass multiplied by its velocity after the collision. And so, because, again, the total force on the system, the total external force is 0, I only have internal forces by collision. This collision makes two forces from M1 and on M2, and vice versa. These forces are action or reaction. They are equal in magnitude, opposite in direction. If I sum these two forces, the value will be 0. So the total force on these two balls will be 0, and that means that the total momentum of this system will be 0, and that means that before the collision, the change in the linear momentum will be 0, and that means the momentum itself will be constant. So before the collision we'll have a value, after the collision we'll have another value, but it's the same. So the momentum before is equal to the momentum after in this case. Okay, from what we have reached so far, in an isolated system, which means no net external forces, we have that the total linear momentum before whatever process, before the collision or before whatever event happens between these objects and before affecting on each other by forces, then the linear momentum before is equal to the total linear momentum after. So the total linear momentum before is the same as the total linear momentum after, and I express it in this way. Okay, the last thing we want to talk about today is the impulse. As the net force on an object is equal to the change of its linear momentum with time, as I told you like in the previous slides, the net force on the system is equal to the change of its momentum during a time, or divided by that time. So I can multiply both sides by delta t, or dt, and I can say, okay, the change in the momentum is equal to the net force on the system multiplied by dt. This dt is the time this force affects on the system to change its kinetic status. So I'm, for example, given a force to this chalkboard eraser. So at the time I'm given the force, during given the force, this is the time, delta t. So when I leave it, I'm not given force no more, delta t is over. So I can touch it for 0.3 second, 0.4 second, or for 1 second, whatever. Like this is the time. During this time of exerting the force, this is the time I'm in here. The time here is the time needed to make the force. So if I multiply my force by delta t, if my force is constant, then this will give me the change in the momentum of that object. This is called the impulse. So the impulse is the external force on the system by delta t, or the change of the value of the momentum. If you know the momentum before and the momentum after, you subtract as vectors. This is equal to the impulse on the system. So F dot dt, which is equal to the change of the linear momentum, is equal to the impulse, which is the same as delta p. Thank you very much.